On April 10, 2019, the European Commission together with the Event Horizon Telescope collaboration unveiled a never-before-seen sight from the universe. A vision from a remote galaxy, a staggering 53 million light-years away. Our focus is drawn to this, the heart of the distant galaxy, M87. The very first image of a supermassive black hole. This remarkable unveiling gives solid proof of this celestial entity, which until then, were only a concept. It allows scientists to measure the black hole's mass more precisely. Who could have guessed that the shape of a black hole is round? Exactly as forecasted by Einstein's theory of relativity? Long ago we didn't know if black holes would be common in the centers of galaxies with the help of the Hubble telescope, which has good precise ways to look down in the center.
Long ago, we didn't know if black holes would be common in the centers of galaxies with the help of the Hubble telescope, which has good, precise ways to look down in the center. Every galaxy we've had the capacity to check has revealed a black hole to us. Thus we will extrapolate and assert that a black hole is a natural phenomenon in the center of all galaxies of the universe. We're ready to delve into the structure of a black hole. An exploration that might reshape our comprehension of the cosmos. Join us on this journey as we seek answers to one of the most important questions in astronomy. Black hole. The dark side of the universe. A black hole is a mysterious and extreme phenomenon in the universe, created from an explosion and enclosing a huge mass at its center. It is a place where the force of gravity is so strong that nothing can escape, not even light. Once something enters a black hole, it stays there forever. Black holes come in many forms, such as stellar black holes, which can be several times the mass of the Sun. Supermassive black holes, on the other hand, can occupy millions or even billions of times the mass of the Sun. These massive objects not only distort space with their mass, but also profoundly affect the flow of time around them. Einstein's theory of relativity is important for understanding the mysterious activity of black holes. It describes how the fabric of spacetime is formed by mass and how it affects time. According to the special theory of Minkowski space, space and time are unified and form four-dimensional spacetime, where 3 dimensions represent space and 1 dimension represents time. When mass enters space, interaction occurs due to increased energy. According to Einstein's theory, space is not flat, but rather curved around objects. In this, gravity does not act as an invisible force, but is instead a consequence of the curvature of spacetime. The force of gravity increases when the density of energy within an object increases. Under this concept comes the emergence of the theoretical concept of black holes, which are created by the collapse of a massive body. In this process, a black hole is created by collapsing to a certain size, known as the Schwarzschild radius. Not only did black holes exist, but Einstein's general relativity provided a unique solution to the formation of black holes. This equation implies that a black hole has 2 main parts. The event horizon, which acts as a boundary between the black hole and the universe, and the inner mass, which gives rise to the existence of the entire mass of the black hole. Thus, a black hole completely consumes the volume of spacetime around it. Can think of a black hole as completely consuming the volume of spacetime in its vicinity.
Secrets of the universe. The study of the universe leads to the discovery of endless mysteries, especially towards special asteroids like black holes. Everything starts with the death of massive stars, when they end with supernova explosions. In this visible scenario, stars eject their outer layers into space, causing gravitational collapse into the center, which is the first step in black hole production. If a massive star is several times more massive than our Sun, its central core is compressed into a larger volume due to gravity. This causes intense pressure to form and the mass to coalesce, which looks like a soft ball. Think of that ball as being more compressed, but its mass remains unchanged. It then becomes denser, as if you were squeezing a golden ball hard, while it shrinks to the size of a grain of sand. Now we look at a real black hole. If the Earth were to become a black hole today, it would have the shape of a plum. But how is the formation process of black holes? Is there a limit, where the black hole can no longer contract? It is associated with the state of matter. A rock holds its shape because energy exists between atoms and molecules, but changes in different ways as pressure increases. Finally, we consider how electrons actually make up matter. When we are under a lot of stress, the electrons move out of place and come together. This condition is known as electron depletion. When two or more electrons try to overlap, they progressively maintain their identity, which is possible in light of the principles of quantum physics. The concept of black holes opens up a new horizon of mystery and beauty of the universe. It reminds us that the universe is not just a place but a giant pothy where mystery and beauty are constantly being built. In the timeless expansion of our universe, this state of extremely dense matter is found in white dwarfs, comparable to the remnant core of the Sun. It is a grand scene, in which the arrangement of an atom's nucleus and its electrons in the midst of vast space symbolizes an incomparably tiny substance. Imagine, if an atom were viewed in the shape of a football stadium, with the nucleus at its center the size of a tiny poppy seed. We learned this revolutionary information from the experiment of Ernest Rutherford. First, he began observing particles in a thin layer of gold and was surprised to find that most of the particles' path was uninterrupted. As a result, he discovered a new truth, which plunged him into deep thought about the consequences of his research. Rumor has it, he was afraid to step on the floor the next morning after getting out of bed. Realized, he knew how empty that vast existence was. In the compression process, electrons are crammed into protons, creating a new beginning amid lost potential. Here it can be seen that when a positive proton combines with a negative electron, a neutral particle is created, called a neutron. The name neutron star is not just a misnomer. Rather, these stars are densely packed with neutrons. When a star is exhausted, these neutron stars remain in their life cycle. These extraordinary cosmic objects are incredibly dense. A spoonful of neutron stars weighs as much as a mountain. It will enter the world without question.
Star matter weighs about a mountain per teaspoonful. So much that if I had a piece of it here and let it go, and I could hardly prevent it from falling, it would effortlessly pass through the Earth like a knife through warm butter.
As neutron stars spin rapidly, they create a magnetic field, which pulsates. This feature is called a pulsar, for which its discoverer, Anthony Hughes, won a Nobel Prize in the 1970s. Think of the density of these neutron stars. Imagine taking the weight of 300 billion elephants together and compressing them into a single point. Why this inevitability can create such a level of density in neutron stars brings us to the brink of the mystery of black holes. Types of black holes. Black holes are mysterious and fascinating things in the universe. They are divided into several types, each with its own shape, formation process and behavior. The best-known black holes are stellar black holes. The mass of these black holes is typically between 3 and 10 solar masses. Whenever a massive star exhausts its nuclear fuel, it collapses under its own gravity. In this process, the star shrinks incredibly, causing the mass to be confined to a tiny volume. Given that, typically, they span several kilometers, their density increases dramatically. Intermediate mass black holes, however, are a bit of a mystery. Their exact masses have not yet been determined, but they are thought to be thousands of times more massive than distant stars. How these black holes are formed is also a question. Two main theories exist. One theory is that one or more stellar black holes come into accretion, and the other is born by collapsing from an existing gas giant conclave. Detecting intermediate mass black holes can be a challenge, but some evidence of their existence has been found. Finally, when it comes to supermassive black holes, they are the largest of the group. Their mass is millions to billions of times greater. These supermassive black holes lie at the center of most galaxies, including our Milky Way. Although no one can conclusively demonstrate how they form, it has also been observed that they grow massively through smaller black holes by consuming material around them. Also, there are variations like charged black holes. Each of these has its own unique characteristics. Two important types of these are Reissner-Nordstrom and Kerr-Newman black holes. Reissner-Nordstrom black holes have electric charge but no spin, which is described by general relativity. Their charge affects the gravitational field but is held in density. Kerr-Newman black holes, on the other hand, possess both charge and spin properties. This, in turn, creates unique effects in the spacetime around them. The gravity of the singularity inside the black hole brings them to completely different origins. Important chapters of black holes. To step inside a black hole is to discover the opposite edge of a universe. The world outside as we know it is quite different, where time and space imply cause and effect. But what happens when a black hole crosses the event horizon changes the whole concept. We then drift into another spacetime dimension, where time and space are interchangeable. According to the Schwarzschild equation, we enter a new reality when we cross a black hole. At this new position the dt coordinate expresses a timeline, and the doctor indicates the state of space. As a result, we arrive at a position where time can move, stand still, or rewind, all in conflict with the free motion of space. Imaginal travel can occur here, and for objects like our bodies this mental world creates a strange afterlife. The strangeness of this new spacetime expands our horizons. When moving toward a singularity inside a black hole, the course of action you take changes rapidly. A crisis begins where you can gain more control over the time dimension, but that goes against the fundamental principles of your existence. A person who has crossed the event horizon drifts in time, dissociating himself from space, even as he moves towards the singularity. So, once inside, there is no going back. The challenges of making significant strides in the vast universe are not diminished but narrowed. Here the singularity may seem an inevitability, extending a path where individuals will drift through time so rapidly that there is always a crisis in constructing their trajectories. So if we think of a black hole as a gate, it seems, it leads to another universe. But can that terrifying and miraculous place really take us to another realm? Ultimately we should ask the question about black holes. What is it really? Does this swapping of spacetime point to the idea of creating a portal to a new mundane realm? A concept that reveals the mysterious truth of our existence, that will help explain the long ribs of our universe? In this endless discussion, the black hole's depth and the passage of time combine to create a unique experience that dramatically changes our perspective. The singularity. The secret of the universe. The concept of singularity is a mysterious and complex subject in the world of physics. This is the point from which the activity of the universe becomes limited. In the presence of the singularity, nothing is determined. Rather, everything visible becomes infinite and vague. The Big Bang singularity is a phenomenon that is at the heart of scientific discoveries in the current world. This event gave rise to the universe, and shows the collapse of our conventional notions of time and space. Singularities also work within black holes. When matter and energy fall into this cavity, their only destination is to enter an infinite contraction of zero volume. This poses a philosophical and mathematical challenge.
When you think about black holes, as far as we can tell, they are a fundamental quality of the world, but you have to include quantum physics to truly understand them, and that's the cutting edge of what's happening right now.
Because Einstein's equations of general relativity fail in their power when the singularity is encountered. This calls our statistics into question and highlights the need for a new theory that combines general relativity with quantum mechanics. When we look at a black hole, one thought comes to our mind. How are we trying to understand it? This research transcends the boundaries of the concepts of space and time and brings before our eyes some scenes from the fantasy film, Interstellar. Through the image we see how gargantua flows into the center of the black hole. There the light creates a perfect dimension and the reality of space-time is deeply intimated. Once a person enters the singularity of a black hole, their experience goes to an extraordinary level. He enters a strange place, where time and space lose physical form. It's like a kind of tesseract, where every moment in the girl's room is present at the same time. All this represents a new reality created by the void and infinite contraction of the singularity. So when we think about entering a black hole,
Einstein's equations were dividing by zero at the singularity. So we all know that as brilliant as Einstein was, and as successful as his general theory of relativity has been, it has limits. And one limit is the center of a black hole, and another limit is the very birth of the universe itself.
the dark side of black holes. The mysteries of the universe are revealed only when black holes and their dark aspects are understood. Regardless of the type of black hole, aspects related to its dark matter challenge our understanding of these deep caverns. It is a special substance, which dominates the visible part of our universe, and is known as darkness because it does not interact with light or any other form of light radiation. We know that this dark matter is important in influencing the structure and properties of the universe. Researchers hypothesize that dark matter plays an important role in the development of a wide range of structures, from galaxies to black holes. Its energy pulls stars and gas as well as other matter towards itself, forming galaxies. As these galaxies evolve, the probability of creating the perfect location for black hole formation increases. Another intriguing theory of dark matter is that it may be related to primordial black holes. If true, these black holes could influence the dynamics of the early universe through their vacuum energy. This helps in the gradual creation of other black holes and galaxies. It is also said that these black holes may be part of dark matter.
There is a suggestion that the black holes themselves could be dark matter, meaning they are invisible and they could populate the universe almost arguably large enough to explain this missing mass, this missing matter.
Meaning they are invisible and capable of creating a vast universe for this missing mass. Astronomers track the motion of stars around black holes, and this helps detect the presence of dark matter. Changes in the motion of the stars are caused by the gravitational pull of the galaxy, which dictates their response. If the observed motion of the star differs from the assumed position, it means the existence of some other force. This is where the search for dark matter can begin. But keep in mind that, although dark matter can be avoided, it is not actually considered to be the main cause of black hole formation. According to current theory, black holes are usually formed by the compression of fine matter from a collapsed nucleus, but rotating and charged black holes may also be related to dark matter in some way. Their high spin and electric charge can make them sources or reservoirs of dark matter particles. This could lead to new insights into the character of the universe and the importance of dark matter. The mystery of Hawking radiation. Hawking radiation is a mesmerizing theory of cosmology that changed our view of black holes. It is an idea introduced by Stephen Hawking that establishes a completely new relationship between quantum mechanics and gravity. This theory suggests that potential particles near a black hole do not annihilate each other, but instead create an incredibly conceivable phenomenon, when one particle collapses and the other escapes. Imagine, the black hole event horizon is in progress. There is a deep mystery lurking in the possibilities of matter and antimatter. Normally they cancel each other out, but with Hawking radiation, an energy fluctuation occurs that redefines the position of this entity. Vacuum problems can lead to quantum theory, and thus expand the limits of our imagination. According to Hawking's theory, black holes are not stable at all. Rather, they are slowly losing their mass. In the process, information inside the black hole is also likely to leak out, which was previously thought to be the case. The destination of this information is still debated among physicists, but the idea is that whatever is read through the black hole has the potential to merge and reconstruct, which is still a mystery.
Physicists believe that because you have this Hawking radiation, at least the energy that falls into a black hole can eventually leak away as that radiation. The really important thing about that is that not only can the energy get out, but the information can get out. This was the other perplexing thing about black holes.
If you collected all the Hawking radiation emitted by a black hole over trillions of years, you could theoretically recover that information. This implies that the light that escapes through the darkness of the black hole actually carries information along with energy. This information does not die in any case, rather they create a security technology of their own and eventually get out. It emerges in a foreign way. Thus, the theory of Hawking radiation opens a new horizon in the deep study of the structure of the universe and our reality. While it has changed our thinking about black holes, it has expanded the boundaries of our imagination. Black hole paradox.
Consequence of this.
If a super being in the far future could collect every bit of Hawking radiation that came off the black hole for trillions and trillions of years and stick it into a giant quantum computer, then they could reconstruct.
The black hole paradox is one of the deepest mysteries of the universe that still baffles scientists today. When Hawking radiation is discussed, the question arises: is information really lost? If a super entity were able to collect every bit of Hawking radiation, it would be possible for them to reconstruct it into a giant quantum computer. This means, it's time to rethink our perception of data loss. When black holes were first imagined, a huge question arose among physicists. Do these strange entities really exist in the universe? Mathematical reasoning suggested their possibility, but real-life evidence was lacking. In 1964, researchers using advanced X-ray satellites detected an invisible source named Cygnus X1, which was emitting strong X-rays. This was a concern for scientists because ordinary stars emit both visible light and X-rays. The discovery of Cygnus X1 sparked a famous bet between physicists Kip Thorne and Stephen Hawking, in which they debated the reliance on data to prove the existence of a black hole.
Whether or not we actually had the data justified for a black hole. So what was the first black hole?
Stellar mass black hole, so 10-ish suns with a star friend, and the black hole is slowly eating material from the star.
Subsequent studies showed that Cygnus X1 is related to another star in a binary system, which helped measure its mass. Around 2021, it was confirmed that Cygnus X1 has a mass 21 times that of our Sun, making it the most massive star mass black hole in the universe. It is informative that black holes rotate at very close to the speed of light. With the Cygnus X1 example,
I published a paper about the X-ray source Cygnus X1, which might be identified with this system that contained HDE 226868. And if so, and if all connected together in this way that we'd fantasized about, then the companion was a black hole.
Event horizon of a black hole. Black holes and their event horizons are literary expeditions, breaking down familiar boundaries of space and time. When we think about these strange gravitational planets, the questions that come to mind are: how can a creature move toward an event horizon, but never cross that boundary? This then creates an experience where they stagnate, from being visible to slowly fading away. This is how the massive energy generated by a black hole has a profound effect on the patterns of spacetime. In light of the holographic principle, we know that all information in the three-dimensional world of a black hole is actually encoded on the two-dimensional surface of its event horizon. The idea is really accepted that the information is not erased from space, but is instead stored in a secret code. We then discuss the ADS-CFT approximation, which essentially produces a space vibe. This scientific discovery helps conserve properties based on many types of positions, which absorb the energy between collisions of black holes. Through this we are able to enjoy a unique world where all truths can be found. Now, when we look at the large and small black holes, it is understood how they store the information inside them, and the small black holes eventually disappear. So, there are some things, which are eventually erased. But preservation of basic information always exists. This raises another curiosity: when we judge black hole insights through conformal field theory, it is capable of storing enough information to ensure that these scientific ideas point us toward a truly special kind of universe, where there is no danger of losing information. And at this point today, many scientific developments have already found an unfolding value for everyone.
where rigorous analysis shows that these tools of physics can be used not only as a tool for research, but also as a criterion for prediction.
A good thing when things go from they often start out as very speculative, then they become something a little bit better than speculative, conjectural, and the end process is they just become a tool of physics. Things that everybody uses all the time because it has a predictive value, a mathematical value.
Black hole and entropy relationship. A black hole is a mysterious cosmic object, defined by mass, charge and spin. Because of their simple structure, black holes are widely discussed in science discourse. The no-hair theory states that the information trapped inside a black hole is gradually lost, leaving only these three properties. This means that understanding the entropy of black holes is crucial, as it opens up a deeper discussion of what the universe looks like in space and time from our perspective. Entropy is an index of the connectivity of an object, which tells how its internal parts can be arranged. For example, to describe the position of a shuffled deck of cards, we need to provide a lot of detail. Thus, when we say that this order has more entropy than an order, understand that this is another view of the definition of a black hole. But unfortunately, for the no-hair theory, we cannot know the details of what lies deep inside a black hole. As a black hole grows, its entropy increases, thereby increasing the amount of hidden information.
As a black hole grows, its entropy increases, okay? So the amount of hidden information increases. And so there's this very tight relationship between actually the surface area of a black hole and the amount of stuff that it's eaten, which corresponds to the amount of information that that black hole is.
A strong correlation exists between a black hole's surface area and its ability to consume food, which corresponds to that natural information hiding. Through quantum field theory, we know that energy can exist in a vacuum. There, pairs of particles and antiparticles are created and disappear. This process can occur inside or outside the black hole, but when it occurs near the event horizon, it is particularly noticeable. Hawking radiation is an important concept through which we understand that black holes can emit energy and shrink over time. This results in a fundamental loss of information, and we lose the ability to determine the specific quantum states of all the particles that make up the black hole. Just as when a book is burned, everything in the book becomes ash and gas, so the information is permanently lost. This is contrary to the usual laws of physics, where information conservation is mandatory.
Right, let's say you burn a book and collect everything that comes out of the book, all the ashes and all the gas and everything. Then in principle, you can reconstruct the book. Not in practice, right? But you can imagine if you collect every single thing and measure it, in principle you can reconstruct the book. Information is conserved in all of physics.
So, when black holes emit energy and disappear in phases, we reach a point where only one fundamental question remains: the exact thing that created it in the first place. The information paradox. A question arises when discussing the mystery and power of life, which is scientifically proven. This is the information paradox. If you measure everything perfectly, you can get an idea of past events and future possibilities. But its implementation is really possible? The existence of black holes is questionable for us. As Stephen Hawking once said, black holes probably destroy information. It can be said that crossing the boundary of a black hole means losing all the information in the universe, which is against the laws of physics.
Breaks pretty much every law of physics, right? Things don't erase information. They scramble it up, make it difficult to read, but they don't destroy it.
Moreover, this information is invaluable, as it helps us map the universe. But scientists are looking for ways to solve this data paradox. Several theories have arisen, one of which is the concept of the Planck shape. According to this idea, black hole information tries to preserve its existence until it reaches the Planck size level. This level is the point at which quantum mechanics and relativity converge, and the concepts that lead to this are advanced. But it's not entirely easy. Planck's form of black hole energy is very small, but the information is enorme. Because of this, it creates a huge confusion, where the information never seems to come out. In fact, it remains a mysterious reservoir inside a black hole. The information releases energy very slowly to reveal this store of information, as the stream of information unfolds over time. Scientists believe that this process may take much longer than the lifetime of the universe. Does being submerged really lead one's life back to some of the eternal curiosities of space and questions of existence? So we can ask why the information paradox is becoming the biggest mystery. Revealing black hole information can challenge conventional values of science and humanity. If the data is not really destroyed, what happens to the movement and consequences of the data? This is a question that will change the way we work in the universe to new perspectives. Evidence of a previous universe. Thinking about the universe's previous lifetimes really piques our curiosity. If this information flowed into our understanding, what would we see? What if those remnants of matter and energy affect events in our current universe? This is a question that raises the mind of every scientist. In 2019, popular scientist Roger Penrose noted in a paper that there is some evidence for earlier cycles in the universe. Research has shown that some unusual features of the universe originate from a supermassive Hawking radiation, which may indicate the existence of a previous universe. It has become clear that the patterns and conditions of previous universes have some importance in shaping our present universe. These unusual features may serve as a link, proving that a former universe transferred some information and energy to our present. Joining the so-called information paradox raises a new solution, which may help find the answer to the existence of this previous universe. So, we are also being led to a new way of thinking, where the information strategy of the universe is an open mystery to us. Information paradox. Again, we find a new perspective on the information paradox, a subject that profoundly challenges the regulations of our universe. A discussion of the entropy of black holes brings us to a strange idea. We know that the surface area of a black hole's event horizon contains information rather than its volume, which we need to look at the holographic principle to understand. From this principle, commercial three-dimensional segmentation easily displays its data in a two-dimensional boundary. In the first episode, we learned that the information contained in a black hole is not necessarily dissipated into light by Hawking radiation. Instead, it boils over the surface of the event horizon, where there is probably no chance of losing information. We must remember that, according to the no-cloning theorem, data can never be duplicated. A difficult reality appears here, where two separate datasets cannot be seen together by a single observer. In the second part, we move on to the notion of black hole perfection. Connections and interactions between data can never be aggregated by multiple audiences. An observer falling into a black hole sees only his own information, effectively a separate image created by an outside observer on the other side. In this range, another idea emerges as the child's universe, where information is not lost but transferred to a new location. In the third episode, we discover the great opportunity to enter a new universe. There is no scientific objection against this, but only our lack of evidence. If an advanced civilization gathers all the verified data on Hawking radiation, they may be able to reconstruct information about black holes. Physicist Brian Cox said that civilization would likely capture all the information from the black hole over a long period of time and store it in a giant quantum computer. In this way, the recovery of information from black holes can create possibilities that we can surprise for that civilization. Telescope. Knowledge of black holes has come to us through sophisticated telescopes. One of these is the very large VRT telescopes at the Paranal Observatory in Chile. These telescopes have 4 separate units, each with a primary mirror of 8.2 meters diameter. As a result, researchers are able to observe mysterious objects in space like black holes in depth. Using high-resolution images and different wavelengths,
you jumped into a black hole, then we do think that if a super being in the far future could collect every bit of Hawking radiation that came off the black hole for trillions and trillions of years and stick it into a giant quantum computer, then they could reconstruct everything that fell in. So actually, in some sense, you come out.
They can track the motion and composition of black holes. The Event Horizon Telescope is also essential for this research. It is a unique network of synchronized radio telescopes, scattered around the world. These telescopes combine to form an Earth-sized virtual telescope, making it possible to observe the black hole from multiple angles. In 2019, this collaboration led to the first direct image of a black hole, confirming Einstein's idea. The gravitational instrument is installed on the VLT and combines the light from 4 telescopes. It acts as an interferometer, which helps analyze various aspects of the environment around the black hole. This allows researchers to analyze the black hole's bounding disk, jets, and gravitational interactions with nearby stars. As the subspecies have unique abilities, they are able to gather valuable information for scientific research. Finally, one of the most advanced telescopes is the Very Large Telescope, or ELT. In the future, it will be the world's largest optical and infrared telescope. With a primary mirror of 39 meters in diameter, it has excellent light-gathering capabilities. In addition to eliminating atmospheric distortions with advanced adaptive optics systems, it will be able to perform in-depth analysis on the relationship between black holes and their galaxies. These telescopes are helping us to discover new mysteries of the universe. Is it science fiction? The line between science fiction and reality is blurring, especially when it comes to black holes. As scientific research continues, the mysterious glow of black holes fuels our imaginations. The unknowns within it raise a new question in our minds. Theories and concepts we have to keep in mind when we want to understand the nature of this giant hole. In 1985, a prominent writer started telling a simple story about black holes where one character falls into a small black hole and emerges from another, which is actually an interesting idea. This dark hole in space, located light years away, is one of the great mysteries of the universe.
Relativity, and you try to come up with some bigger understanding, deeper understanding. String theorists have been all into this. You get a multiverse. We didn't pull that out of our ass. That came out of the equations.
This begs the question, are there black holes elsewhere, not just in our universe? The concept of black holes takes us into the realm of time travel possibilities. In theory, black holes can act as natural time machines. Einstein's theory of relativity says that time can slow down due to gravitational force. Time differences around a black hole can lead us to a new horizon of future travel. What's incomprehensible, isn't it? This unknown adventure is taking us to new horizons. The mystery of time around black holes. A journey in spaceships is reminiscent of great adventures. As it flows around the black hole, the crew preserves themselves with perfect caution, lest the stark void of this tree attract them. However, the strange nature of the time during this journey changes their experience incredibly. When the spacecraft returns, they step into a new world, which is inconsistent with the previous image. The wheel of time that has turned with them does not even match the speed of the Earth. They may find a world where hundreds or thousands of years have passed. It will become a fairy tale journey for them. The lessons black holes teach are not just about changing the weather or the planets, but also about unlocking the mysteries of the universe for us. Scientists will continue to investigate the possibility of time travel and how such strange phenomena occur through sound holes. It sounds surprising to hear all these things in our entire universe, but when we look at the depth of the structure of time, causation and reality, it seems that there is not just one view, but many hints.